Extraction is a purification or a separation technique that is commonly used in organic chemistry labs to separate compounds based on their partition between two media. These two media could be either a polar and a nonpolar solvent or an aqueous and organic solvent, and usually a compound will have higher affinity to stay in one of the solvents over the other, and this is called partitioning, and this leads to the separation of compounds. Extraction can be used to extract a compound from a solid, such as in the extraction of natural products, or it can be used to separate two compounds. So if you have a mixture of two compounds, one of the techniques that can be used in organic chemistry labs to separate them is using extraction. It can be also used to purify products after reactions. So whenever a reaction is over and is done, then the first step after this is to do the workup, which usually consists of extraction of the organic products out of the reaction mixture. So what is the main principle that makes extraction a good separation technique? Extraction is simply based on the fact that compounds have different solubilities and different solvents, and that's why whenever a mixture of solvents is used, then the compound will always migrate or move toward the solvent where it has higher affinity to stay in. And this leads to separation of compounds. The two types of extraction that will be explained will be solid-liquid extraction and liquid-liquid extraction. In solid-liquid extraction, the compound will be extracted from the solid state to the liquid state, and the most common examples are the extraction of tea and coffee. So whenever a tea bag is immersed in hot water, then the solid compound, which consists of the tea components, will start to move out of the solid and dissolve in the liquid phase. And this is an example of a solid liquid extraction. The compounds usually will have higher affinity to be in the liquid phase. That's why they start to get out of the bag and dissolve in the liquid. The second type of extraction is the liquid-liquid extraction. And in liquid-liquid extraction, the two liquids are used, but the most important factor is that those two liquids should be immiscible. That is, they should form a heterogeneous mixture. The most common example that we know in our already everyday life is a mixture of oil and water, which usually form two layers. Solutes will have different solubilities in the different solvents, and that's why the dissolved compound will be partitioned between the two solvents. For example, let's say we added sodium chloride or table salt to this mixture here. We know that sodium chloride, because it's polar, it has high affinity to dissolve and stay in the aqueous layer or in the water layer, whereas it is less soluble or insoluble in the organic layer. So in this case, after adding sodium chloride to this mixture, we will see that sodium chloride will stay or will prefer to stay in the aqueous layer, and it will never stay here, or at least the amount of the sodium chloride which will stay in the organic layer will be very small. Why? Because sodium chloride has high affinity for the aqueous layer over the organic layer, and this is how a liquid-liquid extraction works. So how does liquid-liquid extraction in a lab work? Extraction, first of all, is done using this glassware, which is called the separatory funnel. The separatory funnel, usually the mixture or the solvents are added from the top phase, and then everything which needs to come out is used by opening the tap, which is here. Usually an organic solvent and water, which is usually called the aqueous layer, are used during extraction. The polar compounds will prefer to go to the aqueous layer, and the non-polar compounds will prefer to go to the organic layer. Usually the aqueous layer is the bottom layer and the organic layer is the top one, except when we use halogenated organic solvents such as dichloromethane, such as chloroform, which is HCCl3, or carbon tetrachloride. Usually these solvents are heavier than water, and that's why they go to the bottom. But in most of the cases, water will be the bottom layer and the organic solvent will be the top layer. So let's take an example of a liquid-liquid extraction case. Let's say we have a mixture of acetoaminophene, which is the main component of Tylenol, and sodium chloride. Both compounds will be added to the separatory funnel. Acetoaminophene, which is an organic compound, is soluble in ethyl acetate, which is an organic solvent, and it is insoluble in water. Sodium chloride is soluble in water, but it is not soluble in ethyl acetate. Based on that, upon extraction, so if I added, let's say, those two solvents, this is the aqueous layer, so water is here, and this is the organic layer, so ethyl acetate, which is the organic solvent, is here. Acetoaminophene, which is an organic compound, will prefer to stay in this layer, whereas sodium chloride, which has high affinity to water, will actually stay in the water layer. And this is how can we achieve the separation between acetoaminophene and ACL. Once NaCl and acetoaminophene have moved to their corresponding layers, by just opening this tap, which is here, I can drain the bottom aqueous layer, and this is how I separate my sodium chloride from acetoaminophene. Now, do we usually do the extraction one time, or do we need multiple extraction? Usually multiple extraction is preferred over a single extraction, and this is because of something which is called the partition coefficient. During the extraction, compounds will be partitioned or distributed between two layers. The partitioning degree depends on the relative solubilities of those two compounds in both layers. The partition coefficient K is an indication about the distribution of a compound in both layers. So K is the concentration of the compound in the organic layer over its concentration in the aqueous layer. And as the value of K increases, this means that we have a better or more efficient extraction. Let's say, for example, we have a compound whose partition coefficient is equal to 8. This means that if 8 molecules of this compound are present in the organic layer, then only 1 molecule of this compound will exist in the aqueous layer. And that's why if I could divide the concentration in the organic layer, which is 8, by the concentration in the aqueous layer, which is 1, I will get 8. Or if I have 16 molecules of this compound, then 16 molecules will exist in the organic layer and only 2 will exist in the aqueous layer. So this compound with a partition coefficient of 8 prefers to stay on the organic layer rather than in the aqueous layer by a factor of 8 to by a ratio of 2:8 to 1. And this is how the partition coefficient determines the efficiency of the separation. If the partition coefficient is small, then the compound will be distributed between both layers, and that's why separation will not be good. This is another form of the equation which is mainly used to calculate the mass of the extracted compound in the organic layer versus its mass which stays in the aqueous layer. M0 is the mass in the organic layer, and it is usually equal to the initial mass minus the mass in the aqueous layer. So in this example here, we can always assume that mass organic is actually equal to the initial mass minus x. So x will be the unknown, and by substituting the masses in this equation. So mass initial minus x divided by the volume of the organic layer divided by mass in the aqueous layer, which is x, divided by the volume of the aqueous layer. And now if we solve and find x, then we can know what is the mass of the compound in the aqueous layer and the mass that was extracted to the organic layer. Usually multiple extractions with smaller volumes are more efficient. So if you have the option to do 3 extractions with 20 milliliters versus doing 1 extraction with 60 milliliters, 3 extractions with 20 milliliters will always give you better results. This will always enable you to extract more of your compound from the aqueous layer into the organic layer. So always multiple extractions with smaller volumes are better than single extractions with one volume. These are 2 examples which we can go over right now. So calculate the value of the partition coefficient K. So our unknown is K, and we are given the concentration in the organic layer and the concentration in the aqueous layer. So just concentration on the organic layer is 0.06 divided by 0.01, and the partition coefficient is 6. In the second example, we were given 10 grams, so this is the initial mass of the compound A, which is 10 grams, were dissolved in 100 milliliters of water. So this is a volume of the aqueous layer, which is 100 milliliters. If 20 milliliters of ethylene acetate, so this is the volume of the organic layer, it's 20 milliliters. It's used during extraction. The question is calculate the mass of organic compound A that can be extracted. So K is given, it's equal 8, and the question is calculate the mass in the organic layer. So the unknown is the mass in the organic layer. Using the equation that I used in the previous slide, so K is equal to initial mass minus x, which is the mass in the aqueous layer, divided by the volume of the organic layer, which is 20, over x, which is the mass in the aqueous layer, divided by the volume of the aqueous layer, which is 100, and this whole fraction is equal to 8. Then we can solve for x. So mi minus x over 20 is equal to 8x divided by 100. So this is done by just cross multiplication. And then you can solve for x and find the mass in the aqueous layer, and later on you can, just by plugging in the value of x here and substituting mi by 10, then you can find the mass in the organic layer.